Today I am going to discuss about triiodide. First, look at its Lewis structure. Triiodide has 3 iodine atoms with negative charge. So iodine, it is in the group 7. So it has 7 valence electrons. So there are 3 iodine atoms. So 7 into 3, 21 plus negative charge is equal to 22. So there are 22 electrons available for both. So let us first complete the octet of the outer 2 iodine atoms. Then we have used 16 electrons. So 22 minus 16 means 6 electrons are available. So they should go to the center iodine atoms. So they are available as lone pair. So when we look at the center iodine atom, now it has 3 lone pairs and 2 bonding pairs. So altogether 10 electrons belong to center iodine atom. So it has already exceeded the octet, but it can violate the octet rule because iodine atom has d orbital. So no need to complete its octet. So let us go into charges. I am putting numbers 1, 2 and 3. So if we take iodine number 1, 7 valence electron for all iodine atom. Now when we look at this iodine atom number 1, it has 7 electron belong to itself. When we come to here, 8 electron, we should count only 1 electron from the bond. So there are again 7 electrons. So this will give -1 C. Then we can say the minus charge is going on to the center iodine atom. Now this is the very true structure for triiodide ion. Then we can move into the oxidation numbers. When we look at this iodine atom, it is connected to another iodine atom. So no charge separation can expect. So oxidation number of this iodine atom should be C. But when we go to here, there is a negative charge on the iodine atom, but there are no changes from the 2 sigma bonds. So oxidation number is -1. Again, no charges on this one, and it is connected to iodine atom, so it is going to be C. When we consider the center iodine atom, 3 lone pairs and 2 bonding pairs. That means 5 VACPR pairs. So then we have to look what is the best arrangement that minimizes the repulsion between bonding pairs and lone pairs for this ion. Now this is the geometry. So the lone pairs around the center iodine atom are in one plane. The plane means we can imagine the plane perpendicular to this white pool. And 3 iodine atoms are on the plane of the whiteboard. So this is the plane of the whiteboard, and this is the plane perpendicular to the whiteboard. So it looks a little bit different from these 3 showings, but they are actually in the plane perpendicular to the whiteboard. That means in this plane. So these are the three lone pairs, 1, 2, 3. This one go into the plane of the whiteboard. This come out from the plane of the whiteboard. This is on the plane of the whiteboard. So this is going to call trigonal bipyramid. That means two pyramids connect from their bases. So this is the 3D model for trigonal bipyramidal structure. I have drawn exactly as he described in for triodide. So these three, 1, 2 and 3 represent iodine atoms, and these 1, 2, 3 represent lone pairs. So you can see these three iodine atoms are in single line or straight line. So this plane of these three lone pairs is perpendicular to the plane of the iodine atoms. So we can rotate this and get a idea. Now you can see these three lone pairs come into single plane like this. One, it is hidden here. Now you can see these three lone pairs and also iodine atom can come to one single plane. So it is visible in different way, in different angles. Now this is the way we drawn in early example. So this bond go into the plane, this come out from the plane, this is on the plane, and also these three iodine atom on the plane. Now let us look at the geometry of this triiodine. So we can divide the geometry two parts. First one, bonding geometry. Second one, electron pair geometry. So when we come to the bonding pair geometry, it should be linear, because you can see three iodine atoms are in a straight line. But we consider them with the lone pairs, then that is not going to be in linear position. It should be trigonal bipyramid. So this is important. Triiodine has two geometries. So we have to consider them in terms of bonding pair geometry and electron pair geometry. Now we will look at the iodine atom number 1 first for the hybridization. So it has three lone pairs and one sigma bond. That means it needs 4 hybridized orbitals. So already we can see there are three lone pairs. So we can right away take these orbitals, 1 from S and 3 from P. That means sp3. So this is, I am writing here, iodine 1, sp3 hybridization. Now let us look at the iodine number 2. It has three lone pairs and 2 sigma bonds. Mean that sigma mean bonding pairs. So we have to have 5 hybridized orbitals. So just from S and P orbitals are not enough. So we have to take 1 from D also. So other thing is, this iodine atom has an extra negative charge. So we have to add that electron here also. Otherwise we will not get correct answer. So now I can add that electron to either here or here. But if we add here, then it will p orbital become completely filled, so it cannot be used for bonding. So because of that, I am going to add that electron to here. Then I can take one from S and 3 from B and 1 from D. So this, now you can see 3 lone pairs and single electrons in P and D orbitals. But when they become hybridized, we can say sp3 dehybridization. So these are 3 lone pairs, and these 2 electrons with orbital will be used to make the sigma group. So iodine number 2 has sp3 dehybridization. When they come to iodine 3, it is identical with iodine number 1. So again it is sp3 hybridization.